Hello again. This is a lecture on how to use the method of least squares when solving linear equations. This is a really important application of the ideas of orthogonal projection and orthogonality, which we've been talking about throughout this chapter. So to lead up to it, let's suppose that we are back in chapter 1 and we want to solve a system of linear equations where there are more equations than variables. So here's a very simple example where I have 3 equations and only 2 variables. Now, 3 equations and 2 variables, it should be surprising that there would be a solution, but maybe there is. As it happens, these equations are solvable. You can check it: x equals 3, y equals 4 is the solution. But what happens if the right-hand sides of our equation are gotten by some sort of process that has lots of error in it? So if these are some sort of experimental measurements, so instead of being 7, 11, 15, there's 6.9, 11.2, 15.1. In that case, these equations are not exactly solvable. If you row reduce these 3 equations, you'll get 0 equals 1, so you'll find that there is no solution. And it is not obvious, looking at the row reduction algorithm, that there is a very good approximate solution which almost solves these equations. So the question I want to ask you, and the answer to that question is the method of least squares, is how could I try to find solutions which come as close as possible to solving these equations, even when there is not an exact solution? So in general, we will use the method of least squares when we are trying to solve more equations when we have variables. So our system of equations will look like A times X equals B, where A is a matrix that is taller than it is wide. And here's how the method of least squares will work. So I'll draw you a little picture. Here is the image of A. So think of that as a 2-dimensional thing floating in 3-dimensional space. If B were in the image of A, we could solve our equations exactly. But we're going to imagine that maybe B is not in the image of A. It's just nearby. So here is the vector B. It is close to, but not in, the image of A. What the method of least squares will do is it will find the orthogonal projection of B onto the image of A. So here's that orthogonal projection, call it B star. So B star is the orthogonal projection of B onto the image of A, and then we will solve the equation AX equals B star. Why do we use the orthogonal projection? Because of all points in the image of A, B star, or the orthogonal projection, is the one which is closest to the point B. So if my left hand here is the image of A, a 2-dimensional plane, and if the tip of my index finger here is the vector B, the point on my hand, which is closest to the tip of my index finger, is the point where I go from my index finger to the plane in a straight orthogonal line. That orthogonal projection is the closest point to the vector B on image of A. So this is going to be the closest we can come to a solution. Okay, so what we need to do is we need to compute the orthogonal projection of B onto the image of A. There are 2 ways we could do this computation. One of them uses QR decomposition and one of them doesn't. I'll start with the one that uses QR decomposition. Okay, so suppose we have a QR decomposition. A is Q times R. So that means, remember, that the columns of Q are an orthonormal basis for the image of A, and R is the change of basis matrix that changes us between in this orthonormal basis and this other basis. And here is a QR decomposition for the matrix A in the example that I started the lecture with. And recall that QQ transpose is the matrix of orthogonal projection onto the image of A. So B star is QQ transpose B. And if we do that example, we can compute, we want to solve AX equals B. So we compute that B star is this Q matrix. Here it is. Here's Q. Here is Q transpose. Here is the vector B. And here is the vector B star. And so now my vector B star is in the image of A, so we really can solve these equations. However, you do not want to solve these equations by using the RREF method, because the values on the right-hand side are messy, ugly floating point numbers like you see here. Any sort of round off, and because you have more equations than variables, any sort of round off error will lead you to think that you have no solutions, even though in fact you do. So here's what you should do instead. So we are trying to solve the equation AX equals QQ transpose B. Or in other words, A is QR, so QR equals QQ transpose B. Well, strip off the Q's from both sides. We want RX to be Q transpose B. And since the R matrix is square, it makes sense to invert it. And that tells us that the vector X is R inverse Q transpose B. And so this is the formula that we would use to find X in this first method. I've copied that formula to the top of the board here. I've showed you what happens in our example here. So here is our B vector. Here's Q transpose. Here's R inverse. We get 2.87, 4.10, pretty close to the 3.4 that we found on the first slide of this lecture. And sure enough, if you plug it in, you'll see that these are good approximate solutions to these equations. If you want to know why you might solve equations like this, look at the lecture after this one on data fitting. But for now, I'm going to tell you the other way you could do this computation without QR decomposition. So I've just showed you one way to do the computation with QR decomposition, and I'm going to show you how to also do it without. Okay, so here are the key formulas from the last lecture. Here are alternate formulas which don't talk about Q and R. They only talk about the matrix A. And let's see what's going on in those formulas. So here I've copied those formulas to the top of the board. So remember, B star is the orthogonal projection of B onto the image of A. So let's draw a little picture. Here is the image of A. Here is B. Here is B star. And this vector here is B minus B star. And notice that B minus B star is orthogonal to the image of A. So for any V in the image of A, we have V dot B minus B star is 0, Or in other words, v dot b is the same as v dot b star. So it's not immediately clear why I'm bringing this up, but hopefully at least the statement is clear. If I have some vector v over in the image of A, you will have the same dot product with b star and with b. Okay, what is this good for? Well, in particular, the columns of A are in the image of A. So that tells you that for each column of A, v dot b is v dot b star, or you can write that out as a matrix equation. When I multiply out this product here, A transpose B, A transpose is going to look like a bunch of vectors, dot, 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 each of which is in the image of A. And so when I multiply this out, I'm going to get v1 dot b, v2 dot b, etc. Okay, dot b. And it would be exactly the same thing if we had b star. So again, it may be a little mysterious where I'm heading with this, but before you always buy the equation, A transpose B matches A transpose B star. And now remember, we're trying to solve for X so that B star equals X. So plugging in B star is AX, we want A transpose B to be A transpose AX. Or in other words, X is A transpose A inverse A transpose. And then B star is A times X, so A times that whole thing. And just to be clear, this matrix A over here, that's a rectangular matrix, taller than it is wide. In parentheses, we have the product of something wider than it is tall by something taller than it is wide. And then at the end, we have something wider than it is tall again. And so this product in parentheses is a small square matrix, which is why it makes sense to compute its inverse. One note about this formula, back in chapter 2, we had the formula for the orthogonal projection onto a line. If you had a line spanned by V, the orthogonal projection onto it was V dot X over V dot V times V. So here you can think of this V dot V in the denominator as being this version of this A transpose A inverse. So now we are not projecting onto a line anymore. Now we are projecting onto a higher dimensional subspace, the image of A. But it's a generalization of this earlier formula. This A transpose A inverse, that's the generalization of the V dot V in the denominator. This V dot X, that's the generalization of this A transpose B. And this V, that's the generalization of this A. So back then, I didn't tell you how to project onto something other than a line. Now you know. Okay, so we've given you two formulas. One more moment on the slide before I go on. So I've given you two formulas. The one thing that's nice, obviously the QR formulas look a little bit simpler. Here's the QR formulas again. But they have hidden inside them the whole Gram-Schmidt algorithm. So if you actually are doing, say, hand computation, these formulas are a little bit nicer because they don't involve Gram-Schmidt, yet they're just working with the matrix A originally. On the other hand, for machine computation, especially if you're concerned about numerical stability, there are some advantages to doing it this way. And to be honest, I'm not enough of a numerical analyst to really know when one is better or the other is better. The final thing I want to say is that least squares computation is everywhere, because in any real example, you're probably not computing with exact numbers, you're computing with approximate ones. And so you need to be able to come up with approximate solutions even when there are not exact solutions. So in particular, therefore, every computer algebra system has a least squares command built into it. In Mathematica, that command is called least squares. MATLAB thinks that command is so important, it's given it just a single keystroke. The backward slash is least squares. Think of it as B divided by A. And here's the NumPy command. Now, I've told you that this is really important and useful. I haven't told you any of the ways that it is useful. So take a little break and then watch the third lecture for this week. That third lecture is on data fitting and is one of the main ways in which least squares is used.